Edexcel Core Pure, complex number 6, the exponential form. The exponential form z equals re to the I theta. You may have already met the Maclaurin series expansion for sine theta, cos theta, e to the x. If you haven't done or you haven't seen them for a while, it's worth looking them up and checking over them before you start this section of the course. These Maclaurin power series allow us to express sine theta as a expansion in terms of theta. Cos theta can be expressed in terms of powers of theta. It's worth noting that in the sine theta expansion we have odd powers of theta, and in the cos theta expansion we have even powers of theta, which will become significant in a moment. It can also be shown that this series expansion is also true for complex powers as well. So now we're looking at the expansion of e to the x for a complex power. So we're going to replace the index x with I theta. So this is the expansion for e to the I theta. 1 plus I theta squared over 2 factorial, etc. And now we're just going to simplify this using things like I theta all squared is minus theta squared, I theta all cubed is minus I theta cubed, etc. Once we've simplified it, you can see that alternate terms still contain the I, and that's where we've done the odd power, and the other alternate terms don't contain the imaginary I because that's where we've done an even power. So I squared has become minus 1. So collecting all the even powers together here, all of those are real numbers. If we collect all the odd powers together, they all have a common term of I. So now we can write e to the I theta as cos theta plus I sine theta. This first bracket is the expansion for cos theta, and this second bracket is the expansion for sine theta that we saw on the previous slide. So now we have z can be written as r cos theta plus sine theta, which we've used extensively before, but it can also be summarized very neatly as r e to the I theta. Similarly, z to the minus 1 will be used quite commonly, and that can be written as 1 over r cos theta minus I sine theta, notice the negative sign, or it can be written as r to the minus 1 e to the minus I theta. So now we have this exponential form of a complex number, and we can still see that it has a modulus r and it has an argument theta. So if you are given something like z equals r e to the I theta, it's still representing a complex number where r is the distance from the origin and theta is the direction from the real axis, the positive real axis. So this is a very compact way of expressing a complex number, and it allows De Moivre's theorem to be derived more easily for all rational powers of n by using laws of indices. So here we have our complex number cos theta plus I sine theta that we'd like to raise to the power n, and if we write it in exponential form first, we can see that it becomes e to the I n theta just using laws of indices. And then, using the previous definition of the exponential form, we can express it as cos n theta plus I sine n theta. In the next video, we're going to be looking at using the exponential form of a complex number.